Hi, I'm Aditya Kumar Sharma. I'll be talking about prospects for observation of continuous gravitational waves lensed by the galactic supermassive black hole. This work is done in collaboration with Soumyadeep, Shashwat, and Ajit here at ICTS. So I am sure you've heard a lot about gravitational waves, so I will not be talking about them a lot. But we know that the first detection was made in 2015 by LIGO, and it was a transient event due to the merger of two black holes of around 30 solar masses. And since then, we have had like 3 observing runs, and we have had order of 100 detections of these transient sources from neutron stars and black hole mergers. And even you can see this is a mass, this is a stellar graveyard plot where you can see that the two objects merge and form something else. The blue ones are the ones detected by LIGO, the black holes detected by LIGO, and the muddy yellow ones are the neutron stars that have been detected. Gravitational waves in themselves are very important because this carry source properties. And if you notice in the plot that the mass regime that has been explored by LIGO was not explored by the EM observatories. So it's itself a big achievement and important. But today I won't be talking about these transient sources. I'll be talking about continuous gravitational wave sources. So basically the difference is that for transient sources, your signal lies within the sensitivity band of the detector for a very short period of time, and but they are rather more as in violent sources. But continuous gravitational waves, they are weaker, but they lie in the detector sensitivity band for a relatively like for a very long period of time. So to give an estimate of how weaker, so if the transient event have strain of the order of 10 to the power minus 21, these have strain of the order of 10 to the power minus 25. So what are the sources that we have? So one prominent source is rapidly spinning neutron stars. Galactic, because they are likely to be detected. Because it's weak, we cannot look very far for these signals. And so the strength of continuous gravitational wave signals from neutron stars depends on the quadrupole ellipticity, which characterizes the deformability of the star, as well as the square of the spin frequency. So they are rotating stars, so it depends on the square of the spin frequency, and they are potentially detectable by upcoming detectors. Now, let me give you a lightning review of what gravitational lensing is, because this is also what I'll be talking about. So gravitational lensing in very layman term is just the bending of some wave by the presence of an intervening mass along the line of sight from the source to the observer. And what they do to the signal is that they introduce this additional root mu, which is an amplification factor. And you in the regime of strong lensing, you can even have multiple copies of the same signal that come to you with a time delay. So because of the time delay for transient events, which are very shortly lived events, you have 2 or more copies that are temporarily separated, as in these copies appear as 2 different events, and but they have the same phase evolution. But we have not had any confident detections of lens pairs till now. People even at ICTS have worked on lens pair identification, and Shastri right now is working on something like this with machine learning techniques, but we have not had any such detections. So let's talk about gravitational lens, continuous gravitational waves though. So we were kind of motivated by the idea that maybe some of the continuous gravitational waves that come from galactic neutron stars can be lensed by the galactic supermassive black hole. I will talk about the galactic supermassive black hole in the next slide. And they can be potentially detectable by the 3rd generation detectors. So right now we have proposals for 3G detectors, which will comprise of 2 cosmic explorers and 1 Einstein telescope. So we wanted to investigate, are they detectable even in that case? Right now the prospects are very weak. And why we are so interested in lens continuous gravitational waves is that they not only carry source properties like gravitational waves, there is also imprint of the lens property. So for example, in our case, it would carry information about the length of the central supermassive black hole, as well as the stellar environment around it. And I'll tell you why that is so. So this is observation by the Keck group, where so I'm talking about the galactic lens right now. So they sort of traced a lot of stars in the galactic center for a period of around 2 decades, and tracing the proper motion, they confirmed that there is a supermassive compact object at the center with a mass of around 4.1 million solar masses. This is also what got the Nobel Prize in 2020. Andrea Ghez and Reinhard Genzel were awarded Nobel Prize for this observation. So we consider this to be our lens. We consider this, so this star is called Sagittarius A star. So we consider it to be our point mass lens. There are other kind of lens like galaxies and galaxy clusters, which are extended objects. But for all intents and purposes, you can consider them to be point mass lens. These are some equations that are relevant.
That, you have 10 more minutes.
Okay. So there are some equations which are relevant here. One is the Einstein angle. It's a natural angular scale that comes about in lensing, and for a point mass lens, this is what it is. If the key features that I want you to take away from this is that it depends on the RS. RS is the Schwarzschild radii of the lens. So it's basically 2 times mass in geometrical units, and then there are some distance dependence as well. The image, then you have 2 copies of the signal, so you have 2 different image locations in the sky. The beta is the actual angular position of the source, and the theta plus minus are the 2 apparent positions that are formed by lensing. And then you have magnifications and time delay. Now what I'd like you to take away from the time delay formula is that it depends on the Einstein angle as well as the beta, the source location. So does magnifications, and we'll like I'll try to motivate why I'm pointing it out right now or later. So theta is a natural angular scale that comes about in your problem, and that kind of helps you characterize strong lensing. So events that are strongly lensed. So basically what we do is that we sort of want to see how many neutron stars lie within the this Einstein angle in our galaxy. So those are the events that we expect to be strongly lensed by the presence of this supermassive black hole. And so to give you a cartoonish description of how this looks like, so it's a 2D projection of the Einstein angle, what we call the Einstein cone. It's not exactly a cone, it's sort of a more complicated shape, but we call it the Einstein cone. It's a 2D projection onto the galactic plane, and obviously it's an exaggerated view, it's very small. So the neutron stars, and so think of neutron stars being dotted. The Earth is around 8 kiloparsec away from the galactic center where the lens is, and we sort of look for the neutron stars that lie within this Einstein angle. So how do we do it? So in order to do it, we need astrophysical, we need spatial distributions for neutron stars, and the distributions are themselves not very well known. So we consider a lot of astrophysically motivated distributions that I'll not get into the details of those distributions, but basically the idea is that you sort of populate your neutron stars initially with some distribution, and you give them natal kicks, which is their birth velocities, and then you evolve them under some galactic potentials. You end up at some basically final distribution, and you sort of find the fits and models for those. So we sort of consider 14 different distributions. What you can do is you can seed the neutron stars in the galaxy using these distributions. So there are about 1 billion neutron stars. So you seed 1 billion neutron stars. You want to make statistically relevant statements. So you do it for 1 million iterations, say. So that's a lot of computation. But you look for the neutron stars that lie within the Einstein angle, and it's very computationally it's like not the most elegant way of doing it. It's very brute force method, but you can do something else. You know the probability distribution for the spatial distributions of neutron stars. So what you rather do is that you compute the average within this volume, within this Einstein cone, and it's a very differential volume. So you populate your across your iterations, you populate your neutron stars only within the Einstein angle with this Poisson distribution around the mean. And when you do that, you sort of end up with something like this. Now reverse CDF is basically 1 minus CDF. CDF tells you, for a PDF, CDF tells you how much lies up to that point, right? CDF of 1 is, say, how much lies within 0 to 1. Reverse CDF is how much lies after that. So this is the fraction that will be lensed, and in our convention it is greater than equals to. So the one you read at 1 or 2 is the fraction that will be greater than 2. So we find that order 1 to 10 neutron stars actually are lensed for different distributions. The range is rather large because of the uncertainties involved in the spatial distributions. But the next question we ask is whether these neutron stars will be detectable by the future observing runs. Right now, it's very unlikely to detect them with the current sensitivities that we have. So before we answer that, let's look at the signal. How does the signal look like? So continuous gravitational waves are for spinning neutron stars. They that have deviations from perfect spheres that we model like a triaxial ellipsoid. Basically, the three moment of inertia are different, and that helps us define the ellipticity. They're not transient but persistent sources. And so in the transient source, when you two images came, they came as two different events, not here. The second image would come when the first image is still within the sensitivity band of the detectors, so you can just expect them to interfere, and you will have composite image which can have waveform modulations, which I'll talk to you about later. So basically, it's a monochromatic signal that at the very first, or it's just a frequency of the gravitational wave is twice of the rotation frequency of neutron stars. This is the intrinsic amplitude. As I told, it depends on moment of inertia, ellipticities, and frequency squared. So of everything that is written, what I want you to notice is that there is a mu. When you consider two different images of this continuous phase, there's a mu interference term. The mu interference terms, it's additional amplification to the unlensed signal. So the one within the bracket would be something, would be your unlensed signal. But now because of lensing, you have additional amplification. But you can now tell me, you can now ask that this is completely degenerate with your actual unlensed signal. So there's nothing telling it apart from the lens, telling apart the lens signal from the unlensed one. But it's not exactly true, because your neutron stars, they move, and when they move on the time delay surface, the delta t, which is the time delay between the two images, sort of change. And that's why you can have waveform modulations. Additionally, you have not considered Doppler modulations, which we intend to do later. So now how do we say if a signal is detectable? We basically compute something called the signal to noise ratio. This is given by this formula. This basically, it's an average SNR formula. It depends on something like average of S squared, under root of average of H squared. The one at the bottom is called the noise PSD. This is what changes across different detectors. Like the future detectors will have lesser noise, and that this is what changes between the different detector generations of detectors. So what we do is we compute, we take the moment of inertia to be around 10 to the power 38 kg meter squared, and we take the ellipticity to be 10 to the power minus 7. We kept it very realistic, and we need information about the spin frequencies. So what we do for the spin frequencies is that we take the spin frequencies from the observation of the known pulsars that have been that are made by the ITNF, the Australian Telescope National Facility. We take those frequencies, we take the spin frequency from that distribution. We then compute the SNR based on this formula for all the events that we find across our various iterations. Now you should realize that our galaxy is just one iteration of this million, or maybe like it's just one realization of this iteration. So and we set the SNR threshold to be 4.5. That has a different significance in itself, but it's too technical to get into that detail. And you see the reverse CDF of the SNR. So if you look at the 4.5 threshold SNR, you see that about 0.14 to 0.15 of the total fraction of lensed neutron stars, they sort of have SNRs greater than 4.5. The SNR actually is dominated by the spin. We have very slowly spinning stars as well, so they sort of are not detectable. But those with a high spins, they sort of cross the threshold, and then this is our prospect. So as I pointed out earlier, the prospects for detection with current generation is very low. However, if you read off this plot, with 3G detectors, the probability of detection is 2 to 55%. So it's non-trivial. To give you an idea, realistically, if you look at the current generation prospects, it would be so for a realistic SNR threshold, let's talk about that. It would be at max 1% when this will just reduce to 45%. For a realistic search, we sort of I threw a bit of details of the SNR threshold under the rug, but this is what the numbers look like: 1% and 45%. So this is like a very richer prospect in the future observing runs. What can we do with such a detection? Why are we so excited about it? So I've already pointed out that lensing amplification, it carries additional information like the lens. So and also proper motion of neutron stars on the time delay surface would cause waveform modulations. So that these observations, if made, can be a probe for the proper motion of neutron stars in our galaxy. Systematic study of these modulations can help us independently probe the properties of the Sagittarius A star, which is our central supermassive black hole, the one that was discovered by the Keck group. Also, so I've not talked about something called the, one second. I have not talked about something called the microlensing effects. There are additional microlensing effects that occur because of presence of smaller objects in the vicinity of the central supermassive black hole. But when you have those effects, they produce extra modulations to your signal. And if you have those, so basically this detection, if carefully analyzed, would actually be a probe for the stellar environment of the central of our galactic center. So these are what comprises our future work. And thank you. That's all.
Questions?
Yeah. So already these supermassive black holes, we know how they lens optical signals, right?
Yeah.
So, I mean, can you comment on what would you learn from gravitational waves, which you have not already learned from optical?
Yeah. So we have not had any lens Newton star observation from these optical signals. So we're just looking at another prospect, that can we have a gravitational wave detection? Right? We're not saying anything else. We're just asking this question, that whether these are detectable in gravitational waves as well.
Yeah, I understand that, like I'm trying to, like ask this question about learning about the lens, right? Like you had some statements about learning about the lens.
Yes.
What would you, it's true that we probably don't have neutron star signal, but we do know that the supermassive black hole does lens, like, like other kind of optical signals.
It does, yes. Right.
So from that, like we already know some things. So what would you...
what we know of the supermassive black hole is not from lensing. We know about it because the Keck group actually analyzed the proper motion of stars in the vicinity of this object, and then we know something about it. We don't know anything about it from lensing yet.
Okay.
So it will lens, but we don't know anything about it from lensing perspective.
But okay, my question still stands. Like, wouldn't optical lensing?
Sure, if you have a detection, sure, why not?
Isn't it more probable than?
No, the lensing, it's both of them are equally probable. So it's just that if Newton star is there, it's lensed. Whether it's the optical signal is lensed or gravitational wave signal is lensed, they're lensed with the same probability. They're following the same null geodesics. So they're lensed with the same probability. We're just asking about the detection prospects for gravitational waves. And people have not observed optical lensing in this regard.
But detection, like prospects are, I would have expected that those are better for optical signals.
Might be, but I don't know about those numbers. We are not talking about that, but there have been no detection in the optical signal for the optical EM signal.
Okay.
Aditya, I have a question. So I think it's a continuation of what Loka has asked. So will it serve as an independent probe of, say, the Sagittarius A star, properties of Sagittarius A star?
Yes, it will. It will.
So will there be any ingredient that you will be taking from, let's say, EM observations and putting it into the analysis that you have done?
Right now, we are not talking about that. But if we have an EM observation, it's good to use those observations as well. But they are not. They are none.
Okay, so my next part of the question is: have you are you also planning to include, let's say, spin effects in the lensing? Because
what
Sagittarius,
spin effects? As in what spin
if you're
effects
using spin, are you trying to include spin effects in the lens itself?
We are modeling it as a point mass lens. So right now there's no spin effect.
So when so talking about the lens properties, one would not be able to infer the spin properties of the lens, I guess.
Yes, for this model, no, you won't be able to infer this.
Okay.
But obviously, you can like if you know the lens property, if you can characterize the lens property very well for even a spinning spinning lens, then you use that to find all the magnifications, all those terms, and you use that in your lens template, right? In order to probe that. Right now, we are just talking about point mass lens, and it was a preliminary study to study the prospects of detection. So that doesn't change the prospects a lot, having spin or not.
This is just to answer a question and also possibly Udipta's question. So just adding to what Aditya mentioned. So one thing that you get with gravitational wave signals that you do not get with electromagnetic signals is, so when you have gravitational waves whose wavelength is comparable to the size of the lens, you have additional wave effects. Now, of course, that is not the case for the supermassive black hole itself, but you might have structures around the supermassive black hole, and the method that Aditya is working on would enable us to probe those things. That's one. Another slightly unrelated, it's not directly related to the lens itself, but one thing that is very interesting as from an astrophysical perspective is the kick velocities and the proper motion of the neutron star itself. Now, as Aditya mentioned, if you have a proper motion of the neutron star, it would incur certain waveform modulations. And you can actually learn that through the gravitational lensing of the gravitational waves from the neutron star, which you would not learn from electromagnetic observations. So there are certain additional things that you can learn. Yeah, just wanted to add that.
Okay, with that, let's thank Aditya.